Awesome. Okay, so in our trek to the stars, it is funny every time. So in our little trip that we're taking out into space, yesterday we kind of got ourselves to the edge of the solar system, all right? I didn't get a chance to go through those AU numbers, but I don't know if somebody could well, I don't know if you could Google it, but how many astronomical units is it out to Neptune's orbit? I'm not sure what the number is. I don't even think I could even guess it. But we're not super far away into space, all right? It's not like we are, you know, way out there. The solar system is actually quite a small object, all right? And so now what we want to do is we want to get beyond that solar system. Again, I've already mentioned, we've only sent 2 probes, man-made probes. They're called probes when they're not in orbit, right? So they're not satellites. Satellites are in orbit. So if NASA creates a device that they're going to send out to take a look at something and it's not going to go in orbit, we call it a space probe, okay? So we've sent 2, and these were sent out in the 1970s, all right?
3 billion.
That's what, meters, kilometers? We need a unit here. Number doesn't have any meaning?
MI.
Miles.
Yeah.
I'm not working in miles. Sorry. My brain doesn't work that way. We want it in AU, astronomical units. Okay, so these probes that they sent in the 1970s, they were the first probes to take a look at the other planets, all right? Do you have 30 AU for what?
From Neptune to here.
Okay, 30 AU. So the Earth is 1 AU, so 30 times that distance gets us to the edge of the solar system, okay? So again, we're out there, but we're not like stars crazy out there, okay? And these probes that they sent in the 1970s have been traveling out past all of the planets, and they've been going for what? Almost 50 years, not quite, 40-some years. And they have made it past this Oort cloud and have just made it just outside of what we would call the solar system, past its boundary, all right? There is a boundary because the sun is pushing energy all the way out to the edge of the solar system, and then at some point it becomes so far out that the motion of the sun itself creates this wave as it moves through space, and all of that energy kind of comes to an end, and those probes have just made it past there. They're just outside. And they've been going for, like I said, 40, almost 50 years. So when we talk about going to star, or going outside to the edge of the solar system, we're far out, but we're not crazy far out. Yeah. The probes' cameras, I don't believe, see anymore, but they do have things like magnetic field sensors, all right, to sense if there's like a planet's magnetic field, like our magnetic field that we use for compasses. Do you know what I'm talking about? The Earth has a magnetic field. We're okay with that? Okay. So they can sense that type of thing, and as it left this boundary, it would sense that and send that information back to Earth. So it's been running for a long time. It's not running very well anymore because it's an old piece of technology, but it is sending little tiny bits of data back to Earth. Okay, so we want to really head out there. We want to now get way out there to the closest stars and then further beyond to other stars. So let's first talk a little bit about some distances. How are we going to talk about distances? Because now we are so far away from the sun and the Earth and 30 AU, Neptune, that the unit AU doesn't have any meaning anymore. We might as well be talking about meters because we are now getting so far out that we don't even talk about distances from the Earth to the sun because that's a tiny little distance. So we're way out there at this point. So we need a new unit. And the unit that we use is called the light year. All right? And I don't know if I've had the opportunity to talk about light in this course yet or not. Have I mentioned that light's really fast in another unit? Did we mention that somewhere else? Can't remember if I've had a chance to talk about light. I don't think so. By the way, light's really fast. All right? Sound is slow. The speed of sound is about 300 meters per second. So if you were running a track race and you were at the end of the track, at the end of it, and you saw the poof of the firing gun, it would take about a third of a second for you to hear that. So you'd see the poof, and then a third of a second later, you'd hear the crack later on. Have you ever noticed that before? If you're at a baseball game and you're way up in the nosebleed seats, you see them swing the bat, and then you hear the bat go crack later on. Yep. Lightning is exactly the correct answer as well. Correct. So sound is slow. Light is fast. When lightning goes, it's traveling at 3 times 10 to the 8th meters per second. Remember our scientific notation? That means we put 8 zeros on the back end. It goes so fast that really essentially when lightning strikes, we see it right away. It is taking some time, but the amount of time is so tiny that it's infinitesimal, we say. It's super tiny. So light goes super fast. But if we're talking about super long distances, then it's going to take time for light to get there. So what we're saying is light is not infinitely fast. When you turn on the light in your room, it's not that it poof, just illuminates instantly. It actually takes some time to get across the room, but because your room is so tiny, it looks like it's instant. For the sun's light from the sun to get to us here at 1 AU at the Earth, it takes about 8.5 minutes. All right? 8.5 minutes for the sun's light to get to us. So if some evil genius wanted to shut off the sun to destroy all life on Earth, and they did it, they shut it off, we wouldn't know it for 8.5 minutes. We would be living our lives normally, thinking everything is well, but in actual fact, the sun would have gone out, and there would be a trail of darkness going through space at the speed of light, and then get to us 8.5 minutes later. Okay? All right? So, when a star, let's say a star bursts into life, and they kind of do, they kind of ignite. Where there was no light, now, because it's functioning as a star, there is light, and that light will then travel out from that at that speed. Okay? If we were to let that light travel for an entire year, we would have a certain distance that light is gone. We call that a light year. And it's a length. It's a distance. It's not a time. We measure a distance with light years. Okay. Let's calculate how far a light year is in meters. That means we need an equation that allows us to calculate distances from this speed. All right? The equation you will learn in physics is that the speed of an object is equal to the distance it travels divided by the time in which it's been traveling. Okay? Look at that equation. That looks a lot similar to the equations that we've been using. We could put it in a triangle if we had to rearrange that. What we want to find is the distance the light will travel given the speed and the time. So what will my new equation be after I rearrange this? What do you got, Jess? Very good. V times T. Look at us go. We're becoming little scientists. V times T. The speed of light is 3.0 times 10 to the 8th meters per second. There it is. That's the V. I now need to multiply it by the T. But the problem is the units. What unit do you think I need my time in in order to multiply it with a number that has a unit of meters per second. What unit must I be using in order to do this? Yeah, what do you got? I need seconds. So I need to figure out how many seconds are in a year. Well, that can be done. Get your calculators out, folks. We're going to do a little calculating here. We're just going to do one for today. 1 year. I'm going to just put it as Y, year. That's actually not the technical way in which we write year. The technical way is A. We write 1A for year. Kind of crazy. Why do you think we use A to represent a year? I'm going to put it as Y, but it's an A. It stands for annum. What do you think that means? What does annum mean? No? So let's say, sounds like annual. What does annual mean? Yearly. Yearly. Anniversary. All right? A yearly anniversary. I don't know what that is, what anniversary is. And I always forget it, so I end up in trouble. And the sad thing is my anniversary's on New Year's Eve, so I should remember that more often, don't you think? Okay. 1 year times what? I need to multiply it by something to get down to seconds. So what can I multiply it by? Yep. I don't want to work in months because each month is different. So I don't want to work in months because some months are bigger than others, and so I don't want to work in months. Yep. Weeks? I don't want to work in weeks. Yep. Days. And what is it? 365 days. 365 days. I'm now to date. Yep, we're not going to worry about the little tiny little bit that I know it's 364 point something something. We don't care about that right now. All you smart people. It's me being politically correct. Okay. Now I'm at days. What should we turn that into? Yep. Yeah, let's do that. How many am I multiplying that by? 24 hours. And I'm at hours. Whew. Now what am I going to next? You have an answer, don't you? Because you Googled it. Maybe you're learning a new song. What do we got? Minutes. How many minutes? 60. We're at minutes. Almost there. Now I got to turn those minutes. Yep. Because there's 60 seconds in a minute. I was very concerned there for a moment. Let's put that all together. So our time is 1 times, you don't have to actually press the 1, 365 times 24 times 60 times 60. Rachel, what do you have? It's okay. Big. Just tell me the digits. 3153600. Do we like it?
Google agrees. Hold on a second. Let me just.
Nice. We like it? I really don't know. I really have no idea. 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7. Yeah, I'm okay with that. We like it? We like it? Okay. 3153600. Do we remember how to put the scientific notation in our calculator? Which button do I use for the times 10 to the? Did I show you that at the beginning of the class? It's the EXP button, right? Or the EE button. Oh, I do remember this discussion. I'm having some negative emotions welling up inside of me. We struggled with it. Can we make this calculator do this? Here's how it's going. 3, you don't need to put the 0.0 unless you really want to. Then you have to press the EE or EXP button on your calculator. That's going to put the little times 10 to. Then you're going to put the 8. Then you're going to press times. And then you're going to put 3153600. And we're going to get a really big number. Sorry, 9.946 E times 10 to the 15? 15 or 16. If you got 16, you probably pressed times 10. It means you pressed an extra set of buttons, but it's okay. It's okay. Times 10 to the 15? Times 10 to the 15? What's the unit at this point? Because we multiplied our seconds by meters per second. What's it going to be in? It's not minutes. What does the M stand for when we measure things? Meters. Yep. Yes, she is.
Come to the office for a minute, please.
Oh, no problem. Good times. Okay, pay attention. Take a look. Times 10 to the 15. That is way out there. Remember, an AU was times 10 to the 8th, which means we're at times 10 to the 7, even further than that. We're billions and billions. Right? 10 to the 7 is tens of millions. We're tens of millions out beyond the AU. So a light year is far, okay? It's a grand, great length. There is one larger one that I'm not going to explain to you how you get it because it's a tricky thing. We have one more larger unit that we use sometimes called the parsec, all right? The parsec, all right? And it's a distance. You may have heard it in Star Wars when they talk about Han Solo making the Kessel Run in less than 12 parsecs, but they use it as time, and that's a mistake. That's a Star Wars error. It's a length, and it's about 3.3 light years. So it's a little bigger than a light year. Okay, light years are big. So, listen up. Our closest star, our stellar neighbor to our sun, is Alpha Centauri, and is 4.2 light years out there. 4.2 light years, 4.2 times this. Okay? We haven't talked about galaxies yet, but galaxies are massive structures that contain billions of stars beyond what we're talking today. We'll talk about it tomorrow. And the closest galaxy is 2.6 times 10 to the 6 light years away. So again, we're talking massive distances. So let's think about what that means. Let's say that the evil person who turned off our sun now goes to Alpha Centauri and turns off their sun. How long does it take us for us to know it? How long will it take for that end trail of light to get to us? This is an easy answer. Yep. 4.2 years. Okay? So if a star were to go out in our neighboring galaxy, it would take 2 million years until we see that light disappear. So what that means is, when we look out into space and we see the star's light, that's old light. That light could be 4.2 years old. That light could be 1 million years old. So really, when we look deep into space with a telescope, we are actually looking back in time, because we can only see the light as it gets to us after that great period of time. Okay? It's kind of interesting. So there could be a star that has burnt out, run out of its energy. We're still seeing the light now, but it won't take until that light speed can get that light to us until we see it go out. All right, so we're talking about vast distances. Let's now talk about stellar structure. Stars' structures. So again, we've gotten into our spaceship. Starship. And we've cheated by using some science fiction engines, which on Star Trek they call warp drive. And we travel faster than light, which is against the rules of physics. We can't actually do that. There's no way for us to do that. And we travel out to another star, and we get there in good time. In reality, we can't do that. We can't. There's no way even theoretically, feasible way to get us to actually put a person that far out. We can't even get past Mars well, not Mars, the moon. We can't even get past the moon, for crying out loud. Okay, so I'm going to use our sun as kind of our starting point to talk about stars. Our sun is an average-sized star, all right? When we look out there, we see supermassive ones, and we see some tinier ones, but we're about average, middle kind of size. 2.0 times 10 to the 23 kilograms. That's a big mass, all right? Now, we're going to talk about other stars compared to our sun. We like to compare everything to what we have nearby. So we call that mass 1m with a circle and a dot. The symbol that represents our sun is simply a circle and a dot. There are symbols for all of our planets, but the sun, that's how we represent it when we want to write it quickly. So we call this 1 solar mass, okay? It's about 5 billion years old, middle age. How do we know that? We know the laws of physics. We know speeds at which reactions can take place. We theorize that the sun is, working at a particular rate. It's burning its fuel. And working backwards mathematically, we believe that the sun is about 5 billion years old, okay? Billion is 9 zeros, right? 5 with 9 zeros. It has a particular brightness, just like a light bulb. You have a 20-watt bulb or a 120-watt bulb. Well, the sun is a 3.6 times 10 to the 26 watt bulb, giving off a lot of energy in all directions. We call that the luminosity. Now, it's not necessarily its brightness, because a very bright light bulb, if I take it far away, isn't going to look very bright anymore, is it? So that's how much energy it's giving off, but we don't call that the brightness, because brightness depends also on how far away you are from something. These middle-aged stars are made up mostly of hydrogen. Our universe is made up of predominantly hydrogen, the simplest of all elements, all right? When we talk about the Big Bang Theory, we will talk about why hydrogen was the thing that was created, and then we can talk a little bit later on today about how the other elements are created. Actually, I can talk about it right now. Energy is produced in the center of the star by something called nuclear fusion, all right? The protons in hydrogens, because remember, how many protons are in hydrogen? Oh, how soon we forget. It's quite sad, isn't it? Yep, 1. The protons in hydrogen, well, what's the charge on a proton? Yeah? Yeah, it's 1, but what sign is it? Positive. If 2 hydrogen atoms tried to get close together, what would those positive charges do? Reflect.
Oh, no. Sorry. Repel.
I worked so hard. Okay. Repel. So they don't want to get together. But if you could somehow have a strong enough something to get them really close, they would stick. All right? Because even in a nucleus like helium, you might think that those 2 protons would want to fly apart, but there's a special force in the nucleus that keeps a nucleus together. It's called the nuclear strong force, and I'm not going to get into what that is, but it's the glue that keeps a nucleus together. But you've got to get them close enough so the glue can work. And when it does, they stick together, okay? That's called nuclear fusion. Sticking 2 nuclei together by squeezing them so close. And when that happens, it gives off lots of energy. It's an energy-giving scenario. It's like if you have 2 of those super magnets, the strong magnets that we can have, and you bring them close together, and then you let them go, and they crack. They stick together like crazy. You know what I'm talking about? Those little neodymium magnets that they don't like people to have because when babies eat them, they stick it together in their intestines. No? Anyway, so you've done that before. Let them go. Crack! They give off lots of energy. That's what happens during nuclear fusion. So what happens is the hydrogen gets squeezed together. And when it gets squeezed together and you put two protons together, what does it become? Now I've got a nucleus with two protons in it. What do we know that as? Yep. It's positive, that's the charge. But what's an atom that has a nucleus with two protons in it? Second attempt? Nope. That's a charged atom. I have now created an atom that has two protons in its nucleus. Yep. Okay. Nope, we're not even close. This is I'm going to start crying again. Yep. Helium. Yay. We've created helium. So in the center of a star, hydrogen is being turned into helium. Okay? Hydrogen is being turned into helium. In the middle age of the star, that's all that's happening. When a star gets old and it runs out of hydrogen, the helium can get together and squeeze together. Two helium coming together, what would it make?
Wait, has 10 to the power 26, 26 on periodic table is iron. So iron in the middle? What?
No. That number has nothing to do with anything on the periodic table. But you know what? You have come across a weird thing. This is quite entertaining. If I put the two helium together, what am I going to get? Beryllium. Beryllium. And when it runs out of helium, the beryllium will stick together. What are you going to get? You're going to get oxygen. This is how all of the elements are made. This is how all the elements are made. Now listen up. Listen up. There's a weird thing that happens. You can only squeeze nucleuses together until you get to iron. That has nothing to do with what you picked out. That's a coincidence. You can't squeeze iron atoms together to create heavier ones. It just doesn't work. Different reactions happen. So iron is a super common element because in the star that was here in this region before it exploded to make our planets, it turned all of its hydrogen into iron. And so we've got lots of iron kicking around. Okay. What squeezes them together? Massive pressure. What supplies the pressure to the inside of a star, you think? No. No. What force of nature? Gravity. Excellent. It's gravity. Gravity does the squeezing. Awesome. No. Never said that. Okay, I want you to draw this. And you're going to need that exact amount of circles. Yep. Please draw that. Have you got it drawn? Nice. No, it really doesn't. But they are kind of spaced in a way in which it kind of represents the way we believe it to be. We can't actually see this. By the way, this is as if I've cut a chunk off of the, I've cut it in half and opened up the, what's that? It would be. Okay. No, I gotta go. No, I gotta write. So, center. This is called the core. All right? And the core is super hot. And I've got to cheat. I've got to look at some, the core is 15 billion degrees Celsius. 15 billion degrees Celsius. What's that? How do we know? This one comes from the chemical reaction. So fusion. Yeah. That fusion is happening there. And because we can calculate how much pressure there is. we can calculate it knowing the mass of the object, knowing how gravity behaves, all right, and knowing how it's going to push those atoms together. So we can do a calculation to figure out the pressure, okay? From that density of particles, and knowing that the nuclear fusion is going to happen at a certain speed, because we know nuclear fusion quite well mathematically, we can calculate how much energy is being produced, all right? So knowing how that energy is going to be spread into those atoms, we can tell how fast the atoms will be going, and that's how we can calculate the temperature. It's what we believe to be true based on the laws of physics that we know. We've not stuck like a barbecue thermometer to the center of the sun. That would be awesome, but we have not done that. Okay, so fusion happens here. Next one, all right? Here, we'll put a line here so we can see the difference. The next part is called the radiative zone. Radiative zone, all right? As you can imagine, with all that heat, there's a lot of light, all right? We know that the sun gives off lots of light. In the radiative zone, because everything is so squished, the lights can't go very far, because then it runs into another atom. So the light goes maybe a half a centimeter, runs into something else, and gets stopped. And then that atom has so much energy, it gives off that light again, and it goes another centimeter and is stopped, and another centimeter and is stopped. It goes and starts. So the light gets blocked. I'm going to write down what I want you to know. Light bounces from atom to atom. Light bounces from atom to atom. All right? The light bounces from one atom to the next. And it doesn't do it in a straight line, because when the light takes off again, it's random. So it takes a step forward, and it gets stopped, and then it might take a step this way, then it might take a step this way, then it might go back this way. We have a technical term for it. It's called the random walk. In physics, we call it a random walk. And the light hardly gets anywhere. From our calculations of how thick the atoms are, it's believed that it takes about 1 million years for a little piece of light to be formed in the core to get to the edge of the sun. It takes 1 million years. Then when it gets to the edge, it's able to fly freely in a straight line until it gets to us. And it takes 8.5 minutes to do that. So it leaves the sun, 8.5 minutes, it gets to our eyes, we see the light. That light has been bouncing around inside that star for about 1 million years. That is not a solar flare. That's just light from the sun. That's us seeing the sun. Solar flares are completely different things. Yes? Yes, we are. We are. We don't want it to be too complex. Next, we have the conductive zone. Conductive zone. In the conductive zone, the heat is able to cause bubbles of hot gas to float to the surface. Below that, everything was kind of locked in place. There's lots of atoms, but they're not really moving around a lot. In the conductive zone, due to the heat of the particular thing, and I wish I had the conductive zone at the top, but in the conductive zone, there'll be a hot bubble of gas, just like a hot air balloon. And what does a hot air balloon do? Yep, it rises. Why? Why does the hot air in a balloon rise? Yep, because heat wants to go up. Why does heat want to go up? Yep, it's lighter than the air around it. It's less dense because it's been spread out a little bit. Just like a hot air balloon, this bubble of hot gas will float to the top of the convection zone, where it will then give its heat off to the edge of the sun. It will cool, and when it cools, what will that bubble do? No, it'll fall back down. It'll come back down and pick up some more heat. So there's bubbles of hot gas rising and falling in the conductive zone. areas of hot plasma rise to the surface. Areas of hot plasma rise to the surface. Now, and then they give off their heat and then they sink back down and get more heat. So these bubbles are rising up. If you've ever seen pictures of the sun, right? Let's go to this one. I want the sun. Give me the sun. Solar system. The sun. If you've ever seen pictures of the sun, you've seen this, right? It looks grainy. That's because we're seeing the bubbles rising to the surface. That's why it looks this way. The brighter spots are the hot bubbles that have just got to the top. The darker spots are the cooler bubbles that have given their energy off and are beginning to sink down back to the radiative zone to get more energy. So it looks grainy like this. I'm not going to talk about the prominence. I'm not going to talk about sunspots right now, but that's why it looks grainy. Yeah. You mean a bubble move up and down? That I don't have that information for. I've never learned that one. I don't know that. We could look it up. It would be a theoretical number that scientists have calculated using physics. I'm sure it exists, but I don't know what that timeline is. Yep. Not worried about that right now. Did you have a question? From the Galactic Center. Tomorrow's lesson. Any other questions about the sun? All right. Yep. I'm going to get to that in a moment. Okay. All right. The next one we get to is the photosphere. So right there, I'm talking about this little circle right here. The photosphere. This is the surface of the sun. This is what we see. This is the edge of it. This is where the light goes from taking that random walk and then hitching a ride on a bubble of gas and then taking off without anything in its way at this point, heading to our eyes 8.5 minutes later. So in the photosphere, it's the surface that we can see. It is the surface that we can see. Other things I want to say about it. The light at this point flies straight to us. I'm going to put the light flies. I-E-S. If I did it the other way, I'm talking about the insects, a whole bunch of them. Oh, it's the same? Okay. Flies. I'm just going to put the light flies. I'm not even put straight to us. This is where it takes off and doesn't run into anything else. It just goes on. And one last thing. It is about 5,500 degrees Celsius. Okay. Now, I was going to, you know what, I'm still going to show you. You know how I said I might watch videos and that? I've still got a second half of the lesson to do. No big deal. I got 2 extra days. I was going to show video. So don't worry. We'll take our time. I'm not going to rush through it. So we'll just keep talking about that. I'm going to now talk a little bit about how we know that it's 5,500 degrees Celsius. And I haven't burnt something in a long time, so I feel I want to burn something. This is safe, no need to fear. I know you sometimes a little worried about the burning. So let's take a look at burning something. So we obviously can see the sun's surface. You can look up in the sky and look at the sun for a while. It might give you a little headache, so you don't look for very long because it's got a lot of ultraviolet light. It'll burn you. But we could take a picture of it. We could see it. So why do we think that this is 5,500 degrees Celsius? Well, it has to do with the way hot objects behave. You've probably seen this before. Maybe you haven't, because it used to be that everybody's stoves were made up of those coily heat elements. Now, you still might have a stove like that, but many people have flat top stoves and gas stoves, etc., etc. So if I were to just leave this ball right here, just leave it there, for a really long time, what eventually is going to happen to that ball? Yep. It's going to get red. It's going to glow red. I should have started this hours ago. It might not even, I might not even get it to red at this rate. Could we turn the light off, see if we're getting to some red? Can I do this without causing absolute death and mayhem? Oh, it's like I'm roasting marshmallows, but it's not. It's a big hunk of metal. Ooh. How does that ball appear right now? It appears black. In physics, because we're great at naming things, we call this a black body.
Whoa.
Yeah, because it's black. And we know very well the way black bodies behave. We know that if we get a black body hot enough, that's never going to get red. Should have started hours ago. You can turn the light back on. If I were to get the black body hot enough, it would start to glow red. If I could get it even super hotter with like a better Bunsen burner, what would eventually happen? Does anybody know? It would turn yellow and then white and then blue. So we know, I'm not going to do that. That's hot. We were getting there, but we weren't quite there. So we know that when an object is hot, that it glows at a certain color. We even know mathematically exactly what the colors are for each temperature. So by looking at the color of the sun's light and using the black body radiation equation, we can determine that the sun's surface temperature is 5,500 degrees Celsius. Because we know that physics really well. We know those equations and we can do it. So this is using, again, what we call black body radiation in order to know that particular temperature. Okay, 2 more spheres, and then we will stop there and we'll talk more about other stars tomorrow. So the next sphere here is I'm talking about this little space in here. So the space in there, yep. Yep, the surface, yep. Well, there will have to be a gradient. A gradient means a slow change from that maximum to the minimum. Okay, there has to be, right? There can't be anything else. Does that logically make sense? Knowing the laws of physics, that allows us to predict why the radiative zone behaves the way it does. Because we know that when we have heated atoms at that particular temperature, it's going to behave that way. So we're going to assume that it's going to cool itself in a certain way, and that then allows us to predict the existence of the other zones, because we know the laws of physics really well. So we can apply that to that situation. Does that make sense? Okay? All right. This is called the, and I usually write this one down, the chromosphere. I never write that one down, but I'll write, it's in the textbook. Chromosphere. And I don't even, chrome means color, right? Chromosphere, but we can't see it. The chromosphere is essentially the sun's atmosphere. So it's the thin gas that lives just above the surface of the sun. It's the sun's atmosphere. And this then has a strange situation because it's believed to be 65,000 degrees Celsius. Something strange is happening there. But again, they can sample some of the light that's coming from that and they can get that temperature. And it makes no sense. It seems to be getting hotter now. But this is thin. This is thin atmosphere. It's not thick like the sun. It's like a thin atmosphere. One last surface. I have to draw this last one on. This last thing we can't see until there's a solar eclipse that blocks the entire sun's light because the sun's too bright. But if we can block the sun's light, we see that there's this wispy part. There's this very dim, wispy part that actually kind of sticks off like this and maybe goes out this way, and it's always changing. It's being shed off of the sun, and this is called the corona. This is called the, oops, it's not a CH. This is called the corona, all right? The corona is super thin in that there's hardly any atoms there, but it's super thin, and it's super hot. It's about 2 × 10⁶ degrees Celsius. It is super hot. Now, there's not a lot of energy there because there's not a lot of atoms, but it is a super hot thing. Jewel wants to know, how can it go to being cool and then get super hot? How does the atmosphere get so hot? Well, our atmosphere keeps us warm, all right? So you might think it's that type of an effect. Physicists don't know exactly why, but some think that it's the sound of the sun that is vibrating those particles so violently that it's making them super hot. They believe that it is the acoustic sound, the noise that the conductive zone makes as that hot gas gurgles and bubbles up to the surface. They believe that that sound vibrates through that atmosphere and through that thin gas and makes those atoms move super fast and makes them super hot. I'm not even going to write that down because that's also a theory. It's just an idea. Yes?
So, if they were deeper, like the atmosphere, it's still 11.24.
Yep.
So how fast would you have to go to get
To get out. Now that's not necessarily to get through the atmosphere, but to escape the sun. So you're talking about the escape velocity of the sun. That would mean to leave the sun and leave the solar system and be gone, like those probes. We could calculate it with that equation, and I'm going to stop right here, and I will calculate it with that equation. I don't know what the escape velocity of the sun is. You know what? Just Google it. It'll tell you. We could calculate it, but if you Googled the escape velocity of the sun, it would tell you what that is. But that's not necessarily getting out of the atmosphere. That would be just leaving the solar system and getting as far away as you could from the sun, right? Okay? So that it would have a value. Let me just see if I want to stop there. I want to see what my next slide is. Stellar brightness, you know what? That's a good place to stop. I don't necessarily want to get into that. Yeah, we're almost done. So I'm going to just stop my recording here. And then we will start on stellar brightness and that tomorrow.
42.1 kilometers per second.
So 42 kilometers per second instead of the 11 kilometers per second, right? Yeah. I'm going to escape here. Oh, we're going to get the sun out of the way. Clean that up. Excellent.